All right, this is Module 28, Angle Bisectors of Triangles. Thing to remember from previous modules, what an angle bisector is. It's a ray that divides an angle into two congruent, adjacent, that's kind of the key. They have to be adjacent, meaning they have to be attached by a ray. So adjacent angles. The shortest distance, this is from another previous module, from a point to a line has to be a perpendicular segment. That's another key point here because we're going to be talking about distances in both the notes and in the constructions as well. So, okay, so we have our first angle bisector theorem, our first theorem of this module, and it basically states that if a point is on the bisector of an angle, then it is equidistant, meaning same distance, from the two sides of the angle. So if we are given first that point X is on the bisector of AR, that's first, that we're given that. So we know that the angle is bisected. The thing that we can conclude is that point X is going to be equidistant from both sides of CA and AT. So you can actually draw the segments, and remember they have to be, the distances have to be a perpendicular segment. So the converse is also true because we've been talking about converse, perpendicular bisector, converse. Now we have angle bisectors and angle bisector converse as well. But if we know the reverse, if we know a point is in the interior of an angle and is equidistant from the sides of the angle, then it's going to lie on the bisector of the angle. So the thing we know first is point X is in the interior of an angle and it's equidistant from both the sides of the triangle. What we can conclude is that point X is going to be on the angle bisector. So we know first what's in yellow, and we conclude that it's going to be on the angle bisector. So let's get some application with these, because typically application is better understanding sometimes because the theorems just in words and pictures can be a little challenging. So here's our first example. It says find the measure of angle HFJ. So what do I give you in the diagram? Well, what I give you in the diagram is that JG is perpendicular to GF. I also give you that JH is perpendicular to FH. So we know they're perpendicular. We also know that they're the same. So that means that those are equidistant. So J is equidistant from the sides of the angle. Well, if we know that's the case, if this is 23, that means automatically, because of the equidistant part and the perpendicular, so the distance part, that means this has to be 23 as well, because it bisects. So HFJ is also going to be 23 degrees. So this is it in words, because JG is perpendicular to FG, and JH is perpendicular to FH. And we know that JG's segment is equal to JH's segment length of 8. We also know that FJ bisects angle GFH by the converse, because we knew the distances first, and we knew the perpendicular distances and segments first. That's why it's converse. So automatically, once we know it's converse, that means that your angle is bisected, so it's 23 degrees. Okay, another example, for what value of X does point P lie on the bisector of angle ABC, and what theorem establishes this? Okay, so again, what we're given is we're given that AP's distance is going to be the same as PC's distance, and how do I know their distances? Again, because of the perpendicular segments, the perpendicular lines that are created, or right angles that are created. So what we know from the converse of the angle bisector theorem, P lies on the bisector if P is equidistant from both sides of the angle A. So when AP is equal to CP. And again, AP is equal to CP only is valid if these two create a perpendicular set of lines, or right angles. So they act as distances. Okay, so once we know that, we can say, okay, well, since we know that the distances are the same, we can set them equal to each other to solve for x. We subtract x on both sides, add 6, divide, and we get x is equal to 7. So So we have to find out, we were asked to find out for what value of x does point P lie on the bisector. We found the value of x because they have to be equal. Okay, so if x is equal to 7, then P will lie on the angle bisector, ABC. Okay, I give you a figure labeled as such. We have PS is congruent to SR, and that's all we know. We know QS is a ray that goes through both those two. But we're asked, is there enough information to conclude that QS bisects angle PQR? Well, since we know that PS is congruent to SR, that means that the lengths are equal. But it does not say that the distances to the side of the angle are the same. So actually, we can't show that this is congruent. The main reason is we need to know that the angles that are created here and here are perpendicular to know that they are distances. Since we don't know that, we can't say that this is on the angle bisector or on the angle bisector because it's not equidistant, or it doesn't show that it's equidistant. Okay. In many sports, such as hockey, lacrosse, anything that involves a goaltender, soccer is another one, they always use angles. So here's a real-world application problem. We have a soccer goalie's position relative to the ball and goalpost form congruent angles, as shown. So automatically the angles are labeled congruent. Will the goalie have to move farther to block a shot behind the right goalpost, R, or the left goalpost, L? So we're asked to find the distance from here to here. We need to find and see, is it supposed to be this length or this length? Well, if we know that the angles are bisected, automatically what we can say by the angle bisector theorem, the goalie is equidistant from R and L and needs to move the same distance in either shot. So it really doesn't matter. So that's how this can be used in sports. Again, I know a lot of goaltenders think angles, but maybe not in this regard. So, all right. So now we're getting towards the construction part of the module. And the thing we need to know, remember, points of concurrency, that's where three lines, rays, or segments intersect to form the point of concurrency. We are going to call this a specific name, but the first thing we need to know is the angle bisectors of a triangle theorem. They're going to be equidistant, the same distance from the sides of the triangle. And you can basically think, if you were to cut out this entire part here, like, for example, if I just cut out, just pretend that this is not even existing, we have an angle A, it's bisected, that means that DP's length is going to be the same as PF's length here. And if you did that for all three parts of the triangle, you would have the point of concurrency. So the AP, BP, and CP are the angle bisectors of the triangle ABC. We can conclude that DP, EP, and FP's length are all going to be the same. So we basically apply this angle bisector 3 times, and we'll have a point of concurrency in the triangle. So the point of concurrency has a special name, and we call that the in-center, because it is always going to be inside, in-center, inside the triangle when you construct it. So, and that's the main thing. It always is going to be inside. Because for other constructions, remember, it could be outside, on, or inside. That's for perpendicular bisectors, but for angle bisectors, it's a little different. Always going to be inside. So, a circle drawn using P as the center and distance to one side of the radius will be called the inscribed circle, because inscribed, it is touching all 3 sides of the triangle. So again, if I were to use the distances like a radius of a circle and draw a circle within this triangle, it would touch all 3 sides of the triangle, and we call that the inscribed circle. And we find that by finding all the angle bisectors of the triangle. Okay, this also has some other properties as well, but we're going to get some more mathematical application with this. So in the diagram, P is the in-center. That's the key word, because once you see in-center, like circumcenter, it has a specific property. In-center has a specific property as well. You see it in the directions, you can automatically say, okay, that creates equidistance from the sides, and it's from angle bisectors. So we say of triangle ABC, we know that FC is equal to 12. We know CP is equal to 13. I'm asked to find the measure of EP. Okay. Now this is a little challenging, I will say, because it requires something that maybe you haven't seen for a little while, but it is an Algebra 1 based standard. You have to use what's called the Pythagorean theorem, because we have a right triangle within this. Now, why am I using the Pythagorean theorem for the triangle outlined in red when we're actually trying to find this distance here, EP? Well, the reason I'm doing that is because FP, EP, and DP are all the same length. But I know that we have a right triangle here. I know 13 is the hypotenuse. I know 12 is a leg. And I'm trying to find out what this guy is here. So I can use the right Pythagorean theorem for right triangles, find out what my x value is, and then apply that to EP because it's the same distance. So when I do that, I do PF's length. We don't know. We call it x. We can call it PF. We know the length of FC is 12. We know the length of CP is 13. So we apply the squared, subtract, and then to get rid of the squared, in the second part, or the lower part here, we have to take the square root. And now, usually attached to square root, or always attached to square root, is plus or minus. The reason we only include the plus here is because it's a distance. You never have a negative distance, so you always say that it's going to be plus when using the Pythagorean theorem and finding lengths. So, again, if we know that PF and EP are the same because we know it's the in-center, that means we can say that EP is 5. So, why does PF equal EP? Again, the in-center is equidistant from all three sides of the triangle. And how do we know that? Again, because they tell us it's the in-center. Okay, so compare and contrast in-center versus circumcenter, because they have very similar properties, bisectors, but they're different kinds of bisectors. So let's look and see. Constructed by 3 angle bisectors is in-center, but circumcenter is constructed by 3 perpendicular bisectors. So we're bisecting the segments here. We're bisecting the angles here. What else? In-center creates segments that are equidistant from the in-center to the sides of the triangle. And this is key. You need to know its sides because, again, you can get it mixed up with circumcenter, which is vertices. So you need to know equidistant from sides for angle bisectors, equidistant from vertices when perpendicular bisectors. In-center is always going to be located inside the circle. Circumcenter can be located in multiple different places, outside, inside, or on, if you have a right triangle. So in the past, when I've taught this, these two have typically been the most mixed up. So this is one of the reasons why I put this slide here, so you would hopefully distinguish between the two, because again, when constructions come about, it's going to be important to know that. Okay. So now we're going to do our constructions. And again, we have been talking about angle bisectors, so we're going to construct angle bisectors of a triangle, and the 3 angle bisectors create the in-center, and then we're going to also construct the inscribed circle. So please refer to the video for constructions now.